Yes, good morning, all of you. Now, coming to our subject digital system design through VHDL. Last class, we observed that how to prepare a function for a given combinational circuit, and also we have seen Boolean identities and how to implement Boolean identities using VHDL program. Also, we verified. Now, coming to the next part of the topic is yes. Before going to see actually the properties of Boolean algebra. Now let us see. This is the synthesis result of Boolean identities. So in case of in previous session we have seen that the VHDL program for the Boolean identities. So with Vivado design suite we can generate the synthesis report for that program. So the result is like this. The result is like this. Whatever the Boolean identities programs we have written, from that the Vivado design suite generates this one directly. So here the first part gives y and outputs, the second one gives the y r outputs. Based on our statements, automatically it chooses different buffers between input and outputs. Okay. So what is synthesis report? Synthesis report means generating a gate level netlist. Generating a gate level netlist to our programming instructions is called the synthesis report. Okay, since in case of identities, whether you may get the 0 value, 1 value or same value, okay, so that is the thing you can observe here. Okay, based on the Boolean identities only, this is the synthesis report using Vivado design suite. Then coming to let us observe what are the properties of Boolean algebra on AND, OR and NOT gates. Okay, what are the different properties it supports, and also De Morgan's theorem. Okay, so the different properties are involution property, commutative, associative, distributive, absorption, and finally one important theorem is De Morgan's theorem. Okay, so what is meant by involution? So if you apply an invert twice, if you apply a complement, if you apply a complement operation twice on given variable, it gives the same value. Okay, it gives the same value. Okay, in the commutative property means the order is not important with the given variable. So that in the commutative case you can take x plus y equal to y plus x. Whatever the result of x plus y is same as y plus x. Similarly, on AND operation also, if you apply the commutative, that is the order is not important, like x and y is equal to y and x. Okay. Similarly, in associative case, it is also order but on 3 variables. It also order on 3 variables on logical AND and OR operations. So that if you observe with reference to OR operation, x plus y plus z equal to x plus y plus z. Similarly, on AND gate, the associative property implies x and y and z equal to x and y and z. Okay, so that is on 3 variables. Now order not important, it represents through associative property, and 2 variables order is not important, that represents through commutative property. Whereas in the distributive property case, okay, so both AND and OR operations are distributive. That is, if you observe here x and y plus z or y or z, that equal to x and y or x and z. Okay, so this is the distributive on or operation, distributive on and operation. Okay, then absorption means discarding a variable. Like absorption is discarding a variable. So let us observe x plus x plus xy, so that the result is only x. The result is only, that means y is removed. Similarly, x of x plus y gives x value. That means here the variable y is removed, right? Next, De Morgan's theorem represents. De Morgan's theorem is already you studied it, is also in DELD. So x plus y whole bar equal to x bar y bar. That is the De Morgan's theorem implies the complement of for operation is equal to the AND operation on complements of the variables. Okay, so similarly the complement of AND of two variables equal to the sum operation of complemented inputs. Okay, that is the De Morgan's theorem. So these properties already you studied in DELD. Once again I represented here the different properties like involution, commutative, associative, distributive, absorption property also we have seen, and in addition to those properties De Morgan's theorem also we verified. Now coming to minimization techniques. Many different types of minimization techniques already you studied in DELD. For getting the realization using minimum number of gates, the minimization techniques are very helpful. Okay, it not only reduces the gates, it reduces the cost, occupied area, power consumption. Okay, many advantages we have with the minimization techniques. Okay, so if you see gate level minimization means reducing the number of gates. Reducing the number of gates. So let us take one example circuit. Whatever circuit previously we considered, the same circuit I have taken, and I developed a truth table with reference to this logic diagram. So this is the truth table of this logic diagram. Okay, now the gate level minimization is, if you observe this one, actually the given original circuit consists 6 number of gates, but with the truth table you can understand this. So this is the operation can be done using only one gate. That is, if you observe here, the output is become high when both of inputs are equal to 1. Okay, if from this truth table you can understand that the output is at logic 1 if both of its inputs are at logic 1. So this is a truth table you can have for the AND operation, 2 input AND operation. So this total diagram, whatever 6 gate diagram is there, can be realized using one gate, that is only the AND gate. Okay, similarly, if you suppose if the given function is like this, x bar y plus xy, plus xy. So using Boolean algebra, we can simplify the given function as z equal to just y. Okay, so not actually by observing the given logic function, it needs, for getting the x bar one NOT gate, x bar y is one AND gate, xy is another AND gate. For summing these two product terms, one OR gate is required. So totally OR gate, 2 AND gates, 1 NOT gate. So total 4 gates actually needs to realize this function. But by applying the Boolean algebra identities and properties, the simplified equation is just z equal to y. That means no gate is required here, just buffer is enough. Okay, so that is the gate level minimization. So if you see the minimization example, that is using VHDL coding, for the above network. Okay, first of all I am going to write the entity for the above network. That is, in the programming part case, the first of all you have to write library IEEE followed by opening one package using from that library. That is, so that the statement is use IEEE.standardlogic1164.all. Okay, then entity declaration start with the word entity. Minimization example is port of two inputs, so that one input is X and another input is Y, XY in standard logic, and one output Z out standard logic and entity name. Okay, then coming to architecture part is start with word architecture, then architecture name of entity name is begin. As for the given function, here I preferring data flow style of program because Boolean equation is already available, so that Z is less than equal to not X and Y or X and Y. Okay, so the complementation of X you can get through not operator, and the product of X bar Y using AND gate. The product X between X and Y can be get by logical AND operation through another okay, that is the another second term. Then these two terms using OR operation. Okay, end architecture name. But after getting the synthesis report, okay, first of all RTL structure, that is RTL means register transfer logic. The register transfer logic based on the above program, the synthesis report gives. Okay, as per the program it has two AND gates, one OR gate and NOT gate. Okay, but since with the minimization technique, the output is equal to just Y, so that the minimization, because of that minimization we can see buffers only in between input and outputs, not other gates. Okay, so that is the gate level minimization example of Vivado. Next, coming to another technique is not technique, it is actually the implementation of combinational circuit on the lookup tables, using lookup tables. Okay, so because the lookup table is the one of the or how you can say it is a hot for the CLB, combinational logic block, configurable logic block in FPGA. Configurable logic block, CLBs in FPGA. This is the unit to realize the function. But the realization is happen through LUTs, the lookup tables. Okay, but the lookup table consists RAM type of memory, multiplexers, etc. Okay, so that is the lookup table and CLB. And in the coming class we can see how to implement the given combinational circuits on lookup tables. Okay, now I am going to stop this session. In the next class we can see that implementation on 2 variables, on 3 variables, like with the different structures, right? Thank you.